In this lecture, we'll be discussing a notion of linear transformation. So, what is a linear transformation? It is basically an operation that you perform on the vectors in a vector space. Okay. So, the formal definition goes as this: a linear transformation will represent it by A on a vector space V over a field F is a correspondence. So, linear transformation is essentially a map. The correspondence that assigns to every vector x in the vector space V a vector ax, which is also in the same vector space V. So, linear transformation is essentially a transformation or a map which basically relates every vector in X to a corresponding vector which is operated by making which is obtained by making A operate on the vector X. Okay. In addition to this, this transformation has a property which is following, such that A, when acts on a linear combination of a pair of vectors from the vector space, will give you some vector that is nothing but the same as the scaled version of the linear combination, scaled version of the linear combination of respective transformed vectors. So, let's say that, so first of all, A is a map that takes you from X to a vector denoted by Ax. So, this is the transformation, and both of them belong to the same vector space. In addition to this, if you consider a vector which is a linear combination of two vectors from the vector space, then this is also in the vector space. Obtain another vector, let's say this is W, which is the linear combination of the transformed forms of the vectors x and y respectively. Then it so happens that A acting on the vector V is same as the vector W, or what we can say is when A acts on alpha x plus beta y, the linear combination of two vectors from the vector space, what you essentially get is a linear combination of the respective transformed vectors ax and ay with the same scalars associated with them. Okay, essentially this is a linearity property that you have, homogeneity and divertivity that you satisfy. Okay, so that this entire thing holds for, I'll complete this here, for all xy in the vector space V for all alpha beta in the field F. Okay, so a linear transformation is defined over a vector space. It takes a vector from a vector space and gives you another vector in the same vector space. So let's say that you choose two vectors x and y, both of them belong to the vector space, and you know that x is not equal to y, then does not does not imply that ax and ay are not the same. Okay, So essentially, two different vectors can very well be mapped to the same vector under a given transformation in the vector space. Okay. Make some points. Linear transformation is defined over a vector space so the same linear transformation is also valid for the subspaces of the vector space under consideration. Okay, the same mapping holds. Now, what are the examples that you can think of for linear transforms? P is the set of polynomials uh, with real coefficients. I can express it as x of t such that x of t is equal to alpha I t. Okay, of degree n. Alpha I belongs to is the field that is associated with this. We will consider this to be real. So Pn is the vector space of uh, n degree polynomials, and the associated field that is being considered is real. A, or the the transformation that we are considering is the derivative operation with respect to P. Is this operation a vector space? Okay. So if you take any vector from P, okay, for all x in Pn, A acting on x will give you what? Summation I equal to 1 to n I, sorry, this is 0 to n, I multiplied by alpha I t to the power I minus 1. Right, and this of course belongs to n, the set of the polynomial space of the right. So A is a transformation. How do you prove that it's a linear transform or not? So consider a vector V, which is a linear combination of alpha x and beta y. So x I'll represent as I equal to 0 to n alpha I t to the power I, and y of the vector y I'll represent as beta I t to the power I. Okay, and here the alpha beta all belong to the field. Now given this, what is V? 0 to n alpha I plus beta I, sorry, alpha multiplied by alpha I plus beta multiplied by beta I t to the power I is what V is. Now when A acts on V, what do you get? I equal to 0 to n I plus into this factor into multiplied by t to the power I minus 1. And this I can also express as I equal to 0 to n I alpha I t to the power I minus 1 plus 0 to n I beta I t to the power I minus 1. This is nothing but alpha ax of t plus beta ay of t. So here you essentially started with A acting on alpha x plus beta y, and you ended up proving that this is equal to alpha ax plus beta ay. So derivative operation is a linear transformation. Okay. On the vector space Pn over the field of real numbers. Other examples? Set of, let's say, complex numbers. So it's complex number vector space where the field under consideration is let's say the complex number itself. A is basically the conjugation operation. V is, let's say, okay, let's first define this. So if we take any vector in this vector space, so I can express it as, let's say, A plus JB, where J is the imaginary part. Okay. Now when I say AX, because it's a conjugation operation, this is nothing but I can represent a X star, which is A minus JB. Now what is A alpha of X? Is alpha X conjugate, because alpha belongs to the field of, this is a set of complex numbers. Okay, so this is what we have. Now consider vector V. It's a linear combination of this X and Y. So X, Y belong to the vector space and alpha, beta belong to the corresponding field. What is AV? A acting on the vector V is nothing but the conjugate of this entire thing. It is alpha conjugate X conjugate plus beta conjugate Y conjugate. Okay. Oh, by the way, A acting on X gives you X conjugate, and this belongs to the vector space. So A is a transformation. Okay. Now when you take AV, you get this. Now let's see what is alpha AX plus beta AY. Alpha AX plus beta AY is alpha X conjugate plus beta Y conjugate, right? Note that alpha is not equal to alpha conjugate and beta or alpha equal to alpha conjugate, beta equal to beta conjugate does not hold for all alpha beta from the field under consideration. So A of alpha x plus beta y. So A acting on this linear combination is not equal to alpha ax plus beta ay. Okay. So though A is a transformation, A here is not a linear transformation on the vector space C over the field, which is basically the set of complex numbers. Okay, it is not a linear transform. Now consider the same set of vectors for vector space, except for let us change the field associated with this. So this is a real vector space. Earlier we considered a complex vector. This is a real vector space. Okay. Now in this case, again let define say that A represents the conjugation operation. So for x belonging to the vector space, Ax essentially gives you x conjugate, and this also belongs to the same vector space. So A is a transformation. Now we have to check whether this is a linear transformation. For this, consider vector V, which is a linear combination of two vectors from the vector space. Okay, so x and y belong to V, alpha beta belong to the field. When A operates on this linear combination, it gives a conjugate of the linear combination, which also can be expressed as this. Why? Since alpha conjugate is alpha and beta conjugate is beta, as alpha beta both of them are reals. That is what our underlying field is actually. Also, this is same as writing alpha ax plus beta ay. So what you have here is you started with A acting on alpha x plus beta y, and you ended up showing that the same as alpha ax plus beta y. So here A is a linear transform on the vector space given over the field F, which is the set of real numbers. Okay, so A is a linear transform with respect to this particular vector space. Consider another example. Suppose you have a vector space which is basically the 2 cross 2 matrix and the real 2 cross 2 matrix, and the field is reals. Then, and let us say that A is the transpose operation that you do. Okay, so for x belonging to the vector space, Ax is essentially x transpose, and x transpose is also a 2 cross 2 real matrix, so this belongs to this vector space itself. So A is a transformation only. It is a transformation on the vector space. Now consider vector V, which is a linear combination of two vectors x and y, where x, y belong to the vector space and alpha, beta belong to the field. And please note that field in this case is reals, and the vector space in this case is the 2 cross 2 real matrices, set of 2 cross 2 real matrices. When A acts on this vector V, what we get is essentially the transpose of this, which is alpha x transpose plus beta y transpose. Okay, alpha transpose is alpha and beta transpose is beta, because alpha and beta are just real numbers. And if you notice that this is nothing but same as alpha multiplied by the transformation of x plus beta multiplied by the transformation of y. This holds for all xy, because I have not specified any condition on the xy vectors that I have chosen or the alpha beta scalars that I have chosen. Okay. So what we again started with was a linear combination alpha x plus beta y. A acted on this linear combination, and we found that the result is same as the linear combination of the transformed vectors. So in this case, A is a linear transform on the vector space V, which is the 2 cross 2 real matrix set over a field F, which is the set of real numbers. Okay. Similarly, try to explore other examples of linear transforms. So what you can do is, for example, check if integration is a linear transform on a polynomial space of degree n, where the vector space is over a field R. So this is a real vector space. Okay, you can check this. Check. Similarly, check if for or rather I should give you C2 over the field R, the conjugation operation is linear transform. Check this. What happens when the underlying field is complex? Okay. Now, suppose you have a vector space V. Consider a vector space V over a field F. Suppose you have this. Now what you do is consider a set of linear transformations that are defined on the vector space V. Over a field F. Let this set be denoted by, let us denote it by V subscript. Okay. The set VA over the field F is the same field that is associated with the vector space, is a vector space. Okay. So you have a vector space V associated with which a field is associated. Now you can define linear transforms on this vector space. So find all the linear transforms that can be defined on this vector space. Put them together to have a set of these linear transformations. The set of these linear transformations defined over the vector space V associated with the same field as is associated with the vector space V is a vector space. The set of all linear transforms defined on a vector space is also a vector space itself. Okay, so you can verify that the properties like A plus B belonging to VA when A and B are the two linear transformations will hold. A plus B equal to B plus A, basically the commutation with addition. Then you can verify the associativity. There is a identity element, additive identity element, which is basically the zero transform. I'll explain what zero transform is. Then there is a additive inverse transformation, which when added to the transform gives you back the additive identity element. Along with it, if you take scalars, then you essentially end up succeed this way, same as this. Then you have distributive and you finally have the distributive over the vector addition. Okay. Of course, the closure is also there. So I forgot to mention that closure is there when A belongs to VA and alpha belongs to the field, and here beta also belongs to the field. Okay. Now, what is a zero transformation? What is a zero transformation? Zero transformation is a linear transformation that maps every vector in the vector space to the zero vector. Okay, so 0x will always give you the zero vector. So this guy here is the zero transformation. Similarly, you have a identity transformation, which let us represent by this bold one. This transformation is such that every vector is transformed into itself. So if this transformation acts on a vector, it always gives you back the same vector. So this is known as the identity transformation. Okay. So zero transformation is when every vector maps to the zero vector. Identity transformation is when every vector maps onto itself under the operation of the transformation. Okay. So under the O transformation or the zero transformation, you get the zero vector always from every vector, and under the identity transformation. When the identity transformation acts on a vector, it gives you back the same vector. Okay, these are two special transformations that is associated with every vector space that you can think of. Okay. In addition to this, there are few special properties that we can associate with the linear transform, which we define as product, the product of linear transforms. So, how is this product defined? So, let's say that we have a vector space V and the associated field is F, and suppose there is a transformation A, it is a linear transform, and there is another transformation B, which is a linear transformation. Okay, a linear transform transformation P is said to be a product of A and B when P of X is essentially equal to A acting on the transformed vector Bx. Okay, and this is true for all x in the vector space. So you take a vector x, make P act on it. This is same as first B transforming the vector x to some vector, let's say x dash, and A acting on x dash to give you the same vector as what Px gave you. Okay, so it is this x acted upon by B gives you the vector Bx, and when A acts on it, it gives you, let us label this vector as x dash, and when A acts on x dash, it gives you a vector Ax dash. This is now, if suppose there is a transformation P that, and let us label this vector as V. Okay, Ax dash is nothing but V. And suppose there is a transformation that acts on X and takes you to V, and in this case, P is said to be A, and this has to be true for all X in the vector space. So P is a product of the linear transformations AB. Okay. So what are the properties associated with this? A's product with zero transformation is same as zero's product with a linear transform, which is basically going to give a zero transformation. Similarly, A product with the identity transform is same as the identity transforms product with A is same as the linear transformation itself. Linear transform A's product with the addition of two linear transforms B plus C is same as the addition of the products of the linear transform AB and AC. So this is basically distributed. Similarly, A product BC is same as AB product C. So the product operation of linear transforms is basically associative. Okay, but please note, in general, this won't happen. This will happen. Okay, AB and BA are not, AB equal to BA is not true in data. So I should put it like this. The product AB is equal to BA is not true in general for all linear transforms. Okay. It is not true in general for all linear transforms. Basically, the product operation is not commutative. Product is not commutative. Okay, the product operation is not. In addition to this, let A and B be two non-zero linear transformations. Okay, or I should write for some A and B, which are two non-zero linear transforms, the product AB can be a zero transformation. This essentially means that you take a vector x, B acts on it, gives you Bx. When A acts on it, it always give you the zero vector. It's true for all x in B. So the product AB essentially in this case will become equal to 0 if this happens. And this is possible. Okay. If we have a linear transform A that takes x to a vector Ax, the question is there a linear transform which inverts this operation and takes Ax back to x? Is there a transform that does this for all the vectors in the vector space? And this is what is known as invertibility. Okay, so a linear transform A is invertible if for two unequal vectors the mapping is also not equal, and this is true for all x1 x2 in B. So this is basically something like a one-to-one mapping. For every vector, for one vector, it maps onto only on to one more vector. Okay. And the next is the onto condition. So you know that for us, similar to something, the function map takes a value from a domain and gives it in the range. If you want the function to be invertible, first you need to satisfy the one-to-one mapping. That is, for every element in the domain, there exists an element corresponding element in the range. Okay, and for every element in the range, you will find a corresponding element in the domain or the onto domain. So to every vector y, there corresponds a vector x such that Ax is equal to 1. The first one is the one-to-one condition and the second one is the onto condition. Okay. The inverse of the linear transformation A is often denoted by A inverse, and the property that it carries is the product of A with its inverse is same as the product of the inverse with its A, and it always gives you back the identity transform. So if you take this operation, so this is basically A inverse A, or you take this operation, this is basically A inverse, you always get back the same vector x. So here A inverse is the identity map, and here A inverse A is the identity transformation. Okay, in both cases it is the identity transformation. So here I give you a result which is kind of useful. If A, B and C are linear transformations such that A product B and C product A, both of them are equal to the identity transform, then A is invertible and A inverse is nothing but equal to B and C. So both B and C transformations are equal and they are nothing but the inverse of the transformation. Okay, so this is one way to check whether a transformation is invertible or not. You take the transformation and a product of what you think is to be a inverse, check whether it gives identity or not. Now take the commutation of the product and check whether that is also identity or not. If both of them map to identity, then it means the map under the transformation under consideration is an invertible transformation, and the transformation that you multiplied is basically the inverse. Okay, so the next result that I'll tell you is this. Linear transformation A on a finite dimensional vector space V over a field F is invertible if and only if A acting on x is equal to the 0 vector implies that x equal to x itself is the 0 vector. Okay, or alternatively, so for a linear transform defined on a finite dimensional vector space, if you want to verify whether it is invertible or not, then check that if transformation acting on a vector gives you a 0 vector, then the vector itself has to be the 0 vector. So a linear invertible linear transform defined on a finite dimensional vector space when acting on a zero vector will only give you the zero vector. If it acts on a non-zero vector, it will never give you a zero vector. Okay. Alternatively, what you can do is check this. If every vector in this vector space can be written in the form y equal to ax. So essentially this means that for every vector in the vector space, you should have a corresponding vector so that y is same as the transformed vector. Okay. So now we had stated that invertibility condition, which was, let me go back to that, which was this, that x1 not equal to x2 implies ax1 not equal to ax2, or the one-to-one condition. This is same as stating that ax equal to 0 implies that x is 0. So a acting on a vector, if it gives you a 0 vector, then the vector itself has to be a 0 vector. And then we also have to satisfy the onto condition. So this is a general definition of a linear transformation to be invertible. Okay, for some vector space. Now, when we associate this special thing about a vector space, saying that it is finite dimension, basically the dimension of the vector space is finite. In that case, you either need to check for the one-to-one condition or you need to check for the onto condition. If one of them is satisfied, then the transformation A under consideration is an invertible transform. The reason is the one-to-one condition in case of a finite dimensional vector space immediately implies that the onto condition is also true, and similarly the onto condition when you consider this finite dimensional vector space implies that the one-to-one condition is true. So if one of them is satisfied, you can be confident that for a finite dimensional vector space the given linear transformation is actually invertible. Okay, now how is the inverse related to the product of transformations? So let's say that A and B are two invertible linear transforms and P is the product AB. Then P is invertible. So the product of two invertible linear transformations is always invertible, and P inverse is nothing but AB inverse, which is defined as product of B inverse and A inverse. So essentially it is this. You take a vector x, B acts on it, gives you Bx. Let's call this as x dash. Then A acts on it, gives you x dash. Let's call this V. Now what you do is you make A inverse act on V. So it will give you x dash back. And then you make B inverse act on x dash. It gives you x back. So the inverse of the map AB is same as the product of B inverse and A inverse in this sequence. Okay, because what we had stated a few moments back is the product operation in general is not commutative. Okay, so we'll stop here. Thank you.